Hell.
Chirality and Enantiomers in Organic Chemistry. Hey everyone! Welcome back to our channel. Today, we're diving into the fascinating world of chirality and stereochemistry in organic chemistry. Now, I know that sounds a bit complex, but don't worry. We'll break it down together in a fun and easy way. So, let's get started. First, let's visualize chirality. Imagine you have a left hand. Now, if we take its mirror image, we get a right hand. No matter how hard we try to rotate or shift that left hand, we can never make it look exactly like the right hand. This concept of not being superimposable on its mirror image is what we call chirality. In fact, the term chiral comes from the Greek word for hand. In chemistry, chirality applies to molecules too. A chiral molecule is one that cannot be superimposed on its mirror image. To identify chiral molecules, we often look for chiral centers, most commonly carbon atoms that are bonded to 4 different groups. These are called chiral carbons. Take bromochlorofluoromethane, for example. This molecule has a carbon atom bonded to 4 different groups: bromine, chlorine, fluorine, and hydrogen. This makes it a chiral center and, consequently, a chiral molecule. If we draw its mirror image, we can see that no matter how we rotate it, they will never match up perfectly. These 2 mirror images are known as enantiomers. Now, what's the difference between isomers and stereoisomers? An isomer is a molecule with the same atoms but arranged differently. Stereoisomers, on the other hand, have the same connectivity but differ in their 3-dimensional orientation. This is where stereochemistry comes into play, the study of how the spatial arrangement of atoms affects a molecule's properties. Let's take a closer look at identifying chiral centers. Remember, a chiral carbon must be bonded to 4 different groups. If a carbon is bonded to 2 identical groups, like 2 hydrogens, it cannot be chiral. For instance, if we have a carbon connected to a methyl group, a bromine, a hydrogen, and a hydroxyl group, that carbon is indeed a chiral center. Now, here's a fun fact: not all chiral centers are carbon. While carbon is the most common, other atoms like phosphorus and sulfur can also be chiral. But in organic chemistry, we usually focus on carbon. Okay, let's clarify some terms. When we talk about configuration, we're discussing different structures that require breaking and forming bonds to change. In contrast, conformation refers to different shapes or orientations of the same molecule without breaking any bonds. Think of it like a chair and a boat form of cyclohexane. They're the same molecule, just in different shapes. Now, let's explore symmetry. If a molecule has an axis of symmetry, it's likely not chiral. For example, if we look at a molecule and can draw a line through it that divides it into 2 identical halves, it's not chiral. But if we can't find such a line, then we're dealing with a chiral molecule. To determine the R, rectus, and S, sinister, configurations of chiral molecules, we use the Cahn-Ingold-Prelog (CIP) priority rules, which help assign priorities to the substituents attached to the chiral center. Here's a step-by-step explanation of the process. Identify the chiral center. First, locate the carbon atom or other chiral atom that is bonded to 4 different substituents. This is the atom at which the chirality is determined. Assign priorities using the CIP rules. Assign priorities 1 to 4 to the 4 substituents based on their atomic number. The higher the atomic number, the higher the priority. For example, if one substituent is a chlorine atom, atomic number 17, and another is a carbon atom, atomic number 6, chlorine is given priority 1, and carbon is given priority 2. If 2 substituents have the same atomic number, move to the next atoms in the substituent chain until a difference is found. The substituent with the higher atomic number at the first point of difference gets the higher priority. Orient the molecule. Once the priorities are assigned, orient the molecule so that the lowest priority substituent, priority 4, is positioned away from you, behind the chiral center. Determine the configuration. Clockwise, our configuration if the sequence of the remaining 3 substituents, 1, 2, and 3, is in a clockwise direction, the configuration is designated as R, from the Latin rectus, meaning right. Counterclockwise, S configuration. If the sequence is counterclockwise, the configuration is designated as S, from the Latin sinister, meaning left. L and D designations. The L and D nomenclature is primarily used for amino acids and sugars. In the case of amino acids, the L designation corresponds to the S configuration for most amino acids, except cysteine, which is R, while D corresponds to the R configuration. For sugars, the D and L designations are based on the orientation of the hydroxyl group, OH, on the highest numbered chiral carbon in the Fisher projection. To wrap things up, remember that chirality is all about handedness. If you can't superimpose a molecule on its mirror image, it's chiral. And chiral centers, usually carbon, are key to identifying chiral molecules. Understanding these concepts is crucial in organic chemistry, especially when studying how different molecules interact in biological systems. In summary, chirality arises from the arrangement of atoms around a chiral center, typically a carbon atom bonded to 4 different groups. Examples like chiral carbons in certain alcohols or halides illustrate the concept, while non-chiral examples like chlorocyclopentane C5H9Cl demonstrate the absence of chirality. Understanding these distinctions is essential for studying stereochemistry and its applications in fields such as pharmaceuticals. Thanks for joining us today. If you found this video helpful, give it a thumbs up, subscribe for more content, and check out our other videos on organic chemistry. Happy studying, and see you next.
PharmaPal.